concepts about stereoisomerism and postulates of valence bond theory I have discussed in the previous session of coordination compounds. Now I am going to move with the examples which related to valence bond theory of coordination compounds. The first example I have written, we have a cobalt as a central metal atom and NH3 amine as ligands. We have 6 ligands and the charge of the complex is 3+. So now let me explain using valence bond theory of coordination compounds what kind of hybridization is involved in this particular example, what would be the geometry of the complex and what is the magnetic property and what kind of complex this is. For that, it is very important to understand the postulates or assumptions of valence bond theory better. In simple, let me explain again the postulates of valence bond theory of coordination compounds. Remember that in a coordination compound we have a central metal atom and ligands, and we have a coordinate bond in between central metal atom and ligand. The central metal atom of coordinate complex has to provide vacant orbitals. Remember that. Central metal atom is going to provide the vacant atomic orbitals. And the number of vacant orbitals should be exactly equal to coordination number. Coordination number is nothing but the number of coordinate bonds, and coordinate bonds depends upon number of ligands what we have in a compound. So let us assume we have 6 ligands in the coordination complex and the central metal atom has to provide 6 vacant orbitals. And that does not depends only providing vacant orbital, that depends on what kind of ligand is present. As I classified ligands into 2 different types in case of valence bond theory of coordination compounds, strong ligands and weak ligands. Strong ligands helps in the pairing of electrons against Hund's rule, whereas weak ligands won't helps in the pairing of electrons. And if strong ligand is present, weak ligand is present, based on that the central metal atom is going to provide the vacant orbitals. The ligands must contain orbitals with minimum 1 lone pair of electrons. Actually it depends on the how many number of ligands we have, and it depends again the vacant or empty atomic orbitals provided by the central metal atom. So the vacant atomic orbitals undergo hybridization to produce hybrid orbitals, and once hybrid orbitals are produced, hybrid orbitals of a central metal atom overlap with the filled orbitals of ligands to form coordinate bond. That is how actually the process takes place for the formation of coordinate bond, and then using this process we can identify the geometry based on hybridization and magnetic property based on we have unpaired electrons or not, and whether it is inner orbital complex or outer orbital concept we can say by considering n-1d atomic orbitals are used or nd atomic orbitals are used. So that is how the theory of valence bond theory helps us to know the coordination compounds better. That is the postulates what I have discussed already in the previous session, just I revised. So now I will move with this particular example. So finally I am going to arrive at the kind of hybridization, geometry and magnetic property of this compound. So we have a systematic method of writing to explain these hybridization, geometry and magnetic property of this particular compound using valence bond theory VBT. First what we have to do, we need to identify the central metal atom and we need to identify the ligands. Now I hope you are quite good in identifying that cobalt is a central metal atom and the NH3, 6 NH3 we have, and these are ligands. So first what we have to do, you need to write what is the atomic number of the central metal atom. So I am writing here atomic number of cobalt. So atomic number of cobalt, cobalt actually belongs to D block elements, transition elements in a particular 3D series, and the atomic number of cobalt is 27. Now, let me write the electronic configuration of cobalt whose atomic number is 27, and we are quite good in writing the electronic configuration of 3D series. So now I consider argon, because argon is the nearest noble gas for the cobalt. So argon we have, and the atomic orbitals involved for 3D series are 3d and 4s. So argon number of electrons will be 18. So totally it is 27. Already we have 18 here. Therefore I will be writing 3d7 and 4s2, and 18 plus 7 plus 2 you will be getting 27. So argon 3d7 and 4s2 is the electronic configuration of a cobalt that you should know. The atomic number I have written and electronic configuration of cobalt I have written. But if you consider the example what I have written here, the cobalt, this cobalt is not actually as cobalt itself. So this is central metal ion. So as we know how to know the charge or oxidation number of a cobalt. So since the charge of the whole complex is 3 plus, cat ionic complex, and NH3 is a neutral ligand, therefore 0 I consider. Therefore the oxidation number or the charge of cobalt will be 3 plus. What I am going to say, in this compound we have a cobalt 3 plus, cobalt cat ion we have. So if we have a cobalt cation, and what will be the electronic configuration? Electronic configuration of cobalt 3 plus. So now we are writing electronic configuration of cobalt 3 plus. As we know, cat ions are formed by loss of an electron, and here we have a 3 plus, that indicates from actually the cobalt 3 electrons has been lost. In cobalt we have 7 electrons in 3d and 2 electrons in 4s. Mainly the loss of electron will be from the valence shell. Therefore totally 3 electrons has to be lost. So 2 electron is going to lose from 4s atomic orbital, and 1 more electron is going to lose from 3d. Therefore electronic configuration of cobalt 3 plus will be argon. I need to consider the nearest noble gas, argon, and I am going to write 3d6 and 4s0, because for the cobalt this is electronic configuration. Cobalt 3 plus means 3 electrons has to be lost. Therefore the electronic configuration of cobalt 3 plus in the particular complex is 3d6 and 4s0. It is very important to write the correct electronic configuration of central metal ion. So therefore this is how the basic, as we know, or you can directly write the electronic configuration of cobalt 3 plus will be argon 3d6 and 4s. So now let me draw the atomic orbitals. So let me write here orbitals of cobalt 3 plus. So now we'll apply the theory. As the theory of VBT says that the central metal atom is going to provide the vacant orbitals. So how vacant orbitals are going to be provided? To know that, it is important to draw the atomic orbital structures of CO3 plus. Means I am going to represent the atomic orbitals and we are going to fill the electrons over there. So argon we have the noble gas and we have a 3d and 4s. So let me draw the atomic orbitals of 3d and 4s here. So 3d. So since it is d and 5 atomic orbitals you need to consider. So 3d it is. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 5 we have, and this is for the 3D. And next we have a 4s. And now I am going to consider it for a 4s also. So now this is for the 3D and this is for the 4s. As we know, for s atomic orbital the shape is spherical and we need only 1 atomic orbitals for that. If it is p, the shape is dumbbell shape, px, py, pz, 5 actually, sorry, 3 we need. In case of d, we have dxy, dyz, dzx, dx square minus y square and dz square, 5 atomic orbitals. Therefore 5 boxes I considered. That is from the theory of 3d atomic orbitals and 4s atomic orbitals. Now I have to fill 6 electrons in a 3d atomic orbital, and anyhow we don't have electron in case of a 4s atomic orbital. So now after writing the electronic configuration of central metal atom, central metal ion, it is important to fill the electrons into respective atomic orbitals, and filling of electrons into the atomic orbitals follows some standard rules like Aufbau principle, Pauli's exclusion principle, Hund's rule and extra stability rule. Aufbau principle says that electrons are filled into atomic orbitals in the increasing order of energy. If you consider 3d and 4s and later one 4p, if you consider, if you have electrons, we are supposed to fill the electrons into lower energy level, then higher energy level, then higher energy level. That is the statement of Aufbau principle. Pauli's exclusion principle says that electrons of opposite spin can only be paired. If you have an atomic orbital, only 2 electrons can be filled, maximum 2 electrons can be filled, that too of opposite spin, that we call it as Pauli's exclusion principle. If you consider Hund's rule, if you have set of identical atomic orbitals with respect to energy, atomic orbitals of identical energy, then the pairing of electron stars after each atomic orbitals are filled with 1 electron each, that we call it as Hund's rule. Extra stability rule, half filled atomic orbitals, completely filled atomic orbitals are stable. So all these are the familiar principle or rules used in filling up of electrons into different atomic orbitals. You need to remember that. So if you know that, then we can fill the electrons in very easy manner. So in the 3d atomic orbitals, I have 6 electrons, I have to fill that. So all the 3d atomic orbitals are of identical energy. The energy of 3d is different, the energy of 4s is different, whereas the atomic orbitals of 3d itself is of the same thing. So identical energy atomic orbitals we have, you need to follow the Hund's rule. So therefore 6 electrons we have. So first what I do, in all the atomic orbitals I fill 1 electron each. If all the atomic orbitals are completed, then I go with the pairing of electrons. So 6 electrons I have. So just see how I am going to fill the electrons. So 1 I fill here, 1, 2, 3, 4, 5. Now all the atomic orbitals are filled with 1 electron each. Now we have 1 more electron extra. So now the pairing of electrons starts. Therefore the 1 more electron I am going to write here. So if you know the Hund's rule, it will be easy for you to understand how I have represented electrons in this fashion. In case of 4s, we don't have any electrons. Therefore 4s I keep it as empty. One more very important point according to VBT is central metal atom is going to provide the vacant atomic orbitals. We have vacant atomic orbitals, but remember that the vacant atomic orbitals will be as same as the number of coordination number. Coordination number depends on coordinate bond. Coordinate bond depends on the number of the ligands. In the particular species, we have 6 ligands. So 6 ligands means the 6 NH3 are going to donate 6 lone pair of electrons, and 6 lone pair of electrons we have means the central metal atom is going to provide 6 vacant orbitals. Understand the postulate. Since 6 ligands we have, 6 coordinate bond has to be formed. Therefore the central metal atom cobalt has to provide 6 vacant orbitals. We have only 1. So for that what I do, I consider the higher energy level. After 4s we have a 4p. And for the p, how we used to draw? So for the p, we need to consider 3 atomic orbitals. So now I consider higher energy level, and this will be p, 4p, and p electrons we have, and we don't have any electrons in this case also. Even though if you consider the 4p, we have 1, 2, 3, 4 vacant orbitals we got, but actually we need 6 vacant orbitals. But remember, that is not only the condition that decides the production of vacant orbital. One more factor is you need to see what kind of ligand we have. So we have NH3 ligand. Do you know what kind of NH3 ligand is? NH3 is the best example for strong ligand. Strong ligand pairs the electron against the Hund's rule. This is according to the Hund's rule. So in the presence of a strong ligand like NH3, the pairing of electron takes place against the Hund's rule. So how I can represent that? So now try to understand here. I will write the next step here. So for your reference, let me write that NH3 is strong ligand. NH3 is strong ligand. Electron pairing occurs. Electron pairing occurs against Hund's rule. So how actually the electron pairing occurs? Let me draw that. So this is the atomic orbitals for D. Okay, let me draw the full, and this is for the 4s, and this is for the 4p. For p, I need to consider 3 atomic orbitals, right? And now already we have one pair of electrons and 1, 2, 3, 4, 4 atomic orbitals with singly occupied we have. Now in the presence of NH3, so these singly occupied electrons undergo pairing against Ohm's rule. So for that 4 individual we have, 4 individual means 2 pairs we get. Therefore the pairing of electrons takes place in this manner, that is in presence of strong ligand NH3. So remember that since NH3 is a strong ligand, pairing of electrons starts against the Ohm's rule. Therefore the 4 single electrons we have and that undergo pairing and 2 paired electrons we get. Now you count the number of vacant atomic orbitals: 1, 2, 3, 4, 5, 6 vacant atomic orbitals we got, and that suits that we have 6 ligands also. So this is how in the presence of a strong ligand the pairing of electrons starts, and the vacant orbital provided by the central metal atom is as same as the coordination number. Since the coordination number is 6, therefore 1, 2, 3, 4, 5, 6 vacant orbitals I got here. I am going to represent that. So I will represent in this fashion a kind of dotted box to understand how many vacant orbitals we have. So all these are the vacant orbitals, and the number of vacant orbitals is equals to the number of ligands presence or coordination bond. So these two are of the 3D, therefore this is D2, means 2D we have. This is of a 4s, therefore 1s we have. So 1, 2, 3 of a 4p, therefore this is a P3 we have. Therefore these atomic orbitals undergo D2sp3 hybridization. Therefore I am going to write here D2sp3 hybridization. So after this what happens, we'll see now. So based on coordination number and in presence of strong ligand NH3, the pairing of electrons took, and I got a 6sp3 hybridization is going to take place. So these two are D and this is S and these 3 are P. The energies of these atomic orbitals are different. Energy of D is different, energy of S and P are different, and shape is also different. The S is spherical in shape and P is dumbbell and D is double dumbbell in shape. So we have atomic orbitals of different energy and different shape. So in that case what happens, there will be intermixing of these atomic orbitals and hybrid orbitals are formed, that we call it as hybridization. Intermixing of atomic orbitals of different energy to get hybrid orbitals of identical energy, we call it as hybridization, and the new orbitals they are formed, we call it as hybrid orbitals. So therefore 1, 2, 3, 4, 5, 6 hybrid orbitals we are going to get, and the kind of hybridization is D2sp3 hybridization. So let me write over here, I will continue further here. So 6 we have. 1, 2, 3, 4, 5 and 6. So we got 6 D2sp3 hybrid orbitals. Let me write here, all these are 6 D2sp3 hybrid orbitals. So as we know, in case of hybridization, the number of atomic orbitals involved in intermixing is same as the number of hybrid orbitals produced. So 1, 2, 3, 4, 5, 6 atomic orbitals are going to intermix, means we are going to get 6 hybrid orbitals. That is the postulate of hybridization what we have already studied. Therefore 2D, 1s and 3p atomic orbitals will intermix to produce 6 D2sp3 hybrid orbitals, and these hybrid orbitals I have written here. So initially we have written different D and S and P, since the shape and energy is different. Now the hybrid orbitals what we get, and all these have the same shape and identical energy. So these are going to possess same shape and identical energy, and we get 6 D2sp3 hybrid orbitals. So that is how there will be production of hybrid orbitals, and what kind of hybridization is going to be involved? It depends on the vacant orbitals. D2sp3 hybridization is going to be provided. So that is how, in the presence of a strong ligand and in the presence of the number of a coordinate number, so vacant orbital central metal atom is going to provide the vacant orbital, and these vacant orbital undergo hybridization to produce vacant hybrid orbitals. These are just vacant atomic orbitals, and these are vacant hybrid orbitals. So when we have vacant hybrid orbitals of central metal atom, they are supposed to overlap with the filled orbitals of ligands with electrons. So how many electrons we have? How many ligands we have? 6 ligands we have. So let me write here. So 6 NH3 ligands, 6 NH3 ligands with 6 electron pairs. 6 electron pairs occupy 6 hybrid orbitals. If there is overlapping of hybrid orbitals of central metal atom and filled orbitals of ligand, in that case what happens? All these vacant orbitals are filled with the electrons provided by the ligands. So 6 NH3 ligands we have, means these ligands have 6 pairs of electron, and these 6 pairs of electron are going to occupy the 6 hybrid orbitals. So 6 hybrid orbitals what we have, and electrons are going to be filled over there. So how actually the filling of electrons happens here, and let me draw the structure of that. So here we have a 6. So 6 hybrid orbitals, and 1, 2, 3, 4, 5, 6 hybrid orbitals we have, and all these hybrid orbitals are going to overlap with 6 NH3. Therefore, this is from 1 NH3, this is for the second NH3, this is for the third NH3, similarly 4th NH3 and 5th NH3 and 6th NH3. So this is how all the 6 NH3 are going to provide the electrons to this central metal atom. When there is overlapping of hybrid orbitals of the central metal atom and filled orbitals of the ligand, then actually the coordinate bond is going to be formed. As we know, the ligands are going to donate the lone pair of electrons to the central metal atom, so that the dative or coordinate bond is formed. So how many coordinate bond we got here? We got 6 coordinate bonds. We got 6 coordinate bonds. Why we got 6 coordinate bonds? Because 6 NH3 is going to donate its lone pair of electrons to 6 hybrid orbitals. Therefore 6 coordinate bonds we get. So this is how, in a schematic diagram we represent in this fashion. So 6 coordinate bond, that is how all the hybrid orbitals are filled. So now we'll see what kind of hybridization is involved. As we know, this complex involves a kind of hybridization. What kind of hybridization? D2sp3 hybridization. The name of the hybridization will be D2sp3. Now we'll see what would be the geometry of this complex. In the postulates of VBT, as we know, the geometry of the complex depends on the kind of a hybridization. I have made the list of some hybridization with respect to the geometry. Since we have hybridization D2sp3, the geometry of the complex is octahedral. The geometry of the complex will be octahedral, and we know how actually octahedral structure looks like. In the center we have central metal atom cobalt, and 4 corners of the square are filled with NH3, and 1 NH3 above the plane, 1 NH3 below the plane, to form the octahedral structure. If the hybridization is D2sp3, the geometry of the complex will be octahedral. And we will see what about the magnetic property. What about the magnetic property of this complex? Magnetic property of the complex depends on whether we have unpaired electrons or not. So in case of the previous one, 3D and 4s, in the presence of strong ligands, we have all electrons paired, and these will undergo hybridization. All the atomic orbitals or hybrid orbitals are filled with completely paired electrons. So here we don't have any unpaired electron, and here also we don't have any unpaired electrons. Of course, all these are completely filled itself here. So now I can say, since absence of unpaired electrons, this complex is diamagnetic in nature. This complex is diamagnetic in nature, and this kind of particular complex is inner orbital complex. Inner orbital complex, And we have one more name for that. You can call it as low spin complex also, inner orbital complex, or you can call it as the low spin complex also. We have two names. You can use any one, inner orbital complex and low spin complex. Let me tell you why actually this is inner orbital complex or low spin complex. As I said, if the n-1d atomic orbitals are used and then forms inner orbital complex. If nd atomic orbitals are used, the complex is outer orbital complex. So n minus d, if you observe the electronic configuration of this cobalt, we have 4, this will be n and this will be n minus 1. N minus 1 is 3d. So here the 3d atomic orbitals are used for the hybridization. Since n minus 1, this will be the n minus 1. So here we used that. Since we used n minus d atomic orbitals for the hybridization, therefore the kind of the complex is inner orbital complex. One very important, very simple method I will tell you. The kind of ligand is a strong ligand. So since we have a strong ligands, then ultimately the complex going to be formed is inner orbital complex, and opposite will be the one more kind of complex, that is outer orbital complex. If nd, so in the next examples you will see we have one more d which is not n minus 1. So in that case actually the outer orbital complex is going to be formed, and if you have a weak ligands, in that case also the outer orbital complex is formed. So this particular example is inner orbital complex or low spin complex. We can remember this is how we arrive at hybridization, geometry and magnetic property of the given complex CONH3. 6 times the charge of the complex is 3+. First we need to write the atomic number of a central metal atom and the electronic configuration. What is the charge or oxidation number of central metal atom you need to remember, and respective electronic configuration you are supposed to write. And you need to fill the electrons as it is by following the rules. Identify whether the ligand is a strong ligand or weak ligand. Strong ligand, pairing of electrons occurs, weak ligand no pairing of electrons occurs, and depending on the coordination number you need to identify how many vacant orbitals we have, and that many hybridization are going to happen, and that many actually hybrid orbitals is going to be occurred. The how many ligands we have, so these ligands will donate pair of electrons to the hybrid orbitals so that the respective coordinate bond is going to be formed. So hybridization depends on what kind of hybridization we consider, geometry depends on the hybridization, magnetic property depends on presence or absence of unpaired electrons, and inner orbital complex or outer orbital complex, that depends on if you consider n minus d atomic orbital or nd atomic orbital. That is how we arrived at hybridization, magnetic property and geometry of this particular compound using valence bond theory. Example number 2, CO as central metal atom, fluorido F6 we have, and the charge of the complex is 3-. We'll find out hybridization, geometry and magnetic property of this particular complex using valence bond theory. The same procedure has to be followed. First, identify the central metal atom, and cobalt we have. Atomic number of cobalt is 27 we know, and electronic configuration of cobalt, let me write, and electronic configuration is argon, the nearest noble gas, and 3d and 4s atomic orbitals are used. Argon will be 18, therefore 3d 7 and 4s 2 I am going to consider. That is the electronic configuration of cobalt. Now we'll see what is the oxidation number or the charge of cobalt as a central metal ion in the particular complex. This is anionic complex, isn't it? So anionic complex we have, and fluorido the charge is 1-, and totally we have a 6-. 6- will be the charge of that, and then if the charge of this particular F6 is 6- and the cobalt should be 3+, therefore 3 minus 6 you will be getting a -3. That is how we identify the oxidation number of cobalt. Now in this compound the cobalt will be present as a CO3+, therefore electronic configuration of cobalt 3+ will be, as we know, 3+, 3 electrons has to be lost, therefore argon I consider 2 electrons from S and 1 electron from D, therefore the electronic configuration will be 3d6 and 4s0. That is the electronic configuration of a cobalt 3+ in this particular compound. Now what we do next, we write the orbitals for that one. So orbitals of cobalt 3 plus, and we have a 3d. So therefore I need to consider 5 atomic orbitals. So 1, 2, 3, 4, and this will be 5. Next we have a S. So for S we need to consider only 1. So now what I do, I fill the electrons according to the rules. In a d atomic orbital we have 6 electrons. Therefore 1, 2, 3, 4, 5. Now the pairing of electrons starts. So this will be the 6. The theory of VBT says that the number of vacant orbitals provided by the central metal atom should be as same as the coordination number. In this complex, the coordination number is 6. We need 6 vacant orbitals. We have only 1. We need 5 more. And one more factor is what kind of ligand we have. The ligand we have is fluorido F minus. Do you know what kind of ligand it is? Whether it is strong ligand or weak ligand? F minus is weak ligand. So if we have a weak ligand in a complex, then the pairing of electrons won't occur against Hund's rule. It follows the Hund's rule. The atomic orbitals and the filling up of electrons will be as it is. If I consider NH3, these 4 are going to pair up, but I have F minus, therefore there will be no pairing of electrons since F minus belongs to weak ligand. So we have only 1 ligand, so we need 5 more. For that I consider higher energy levels. So this will be actually 3D, we know that, and this will be 4s. I consider next higher energy level will be 4p. Therefore for 4p I consider, so for 4p we have a 3. And if I consider 4p, 1, 2, 3, 4 we have. The 4 is not enough. We need 6. Therefore, higher energy level of a 4p, that is a 4d. And we know that one, how actually we consider the electronic configuration. Therefore, here also, I need to consider d. Therefore, 1, 2, 3, 4, 5 we got. And this will be 4d. Now, 1, 2, 3, 4. 5, 6, 7, 8, 9 we have, but since the coordination number is only 6 and we are required with only 6 vacant orbitals. So how actually this happens? So let me draw it for that one. So F minus, remember in the formula COF is 6, but actually the F will be in the form of F minus. F minus is weak ligand. F minus is weak ligand. Electron pairing does not occurs. Electron pairing does not occurs. So this will be as it is. So let me draw that one. How actually these will be as it is. So you have as it is the 3D. There will be no electron pairing. 1, 2, 3, 4, 5. And let me draw the all first. So we have 4s over here. And the next what I am going to draw, that is for the P. For P we have a 3, Px, Py, Pz, and for the D we have a 5. Let me draw that one. So this will be for the D, in particular 4D. 1, 2, 3, 4 and 5. So now here the electron pair will be as it is. There will be no pairing of electrons since F minus is a weak ligand. So now all these are the vacant orbitals, but the vacant orbitals provided by the central metal atom should be as same as the coordination number. Since coordination number is 6, therefore 1, 2, 3, 4, 5, 6. Only these vacant atomic orbitals are used. So I will represent that in this fashion to understand it better. So we are interested in only these. So we will leave the corner 3 atomic orbitals as it is. So we have 1, 2, 3, 4, 5, 6. 6 vacant orbitals of the cobalt 3 plus we are supposed to use since we have the coordination number 6. So how actually? So this is of the S. Therefore we have a S, isn't it? So this is of the 4s. We have 1 S. And these 3 are P. How many P we have? We have a P3. So in case of D, we have only 2. Therefore D2, the kind of hybridization will be DsP3 D2, DsP3 D2 hybridization. So this is how we can predict the hybridization involved in this case. So what happens after this? So now you remember there will be no pairing of electrons because of F minus. Therefore 6 vacant orbitals I need. Therefore sp3 d2 hybridization is going to occur. So 1s, 3p and 2d atomic orbitals are of different energy and different shape. Intermixing of these atomic orbitals will occur to provide the hybrid orbitals. So hybrid orbitals, how many hybrid orbitals? That depends on as same as the number of atomic orbitals. So 1, 2, 3, 4, 5, 6. Therefore 6 I am going to draw here. So 6 hybrid orbitals. So 1, 2, 3, 4, 5, 6. So all these are actually 6. And what kind of hybrid orbitals? sp3 d2 hybrid orbitals. sp3 d2 hybrid orbitals. So now we got 6 sp3 d2 hybrid orbitals from central metal atom, that is cobalt 3 plus. Now we'll look over it what kind of ligand we have. So we have a F minus ligand, 6 fluorido ligands we have, and these have 6 lone pair of electrons for the donation. Therefore all these hybrid orbitals are filled with 6 pairs of electrons donated by the ligand F minus. So how I am supposed to write that? So now what I write here, 6 F minus ligands, 6 F minus ligands occupy 6 F minus ligands with 6 electron pairs, with 6 electron pairs occupy 6 hybrid orbitals, 6 hybrid orbitals. So let me draw the 6 hybrid orbitals of the central metal atom. So all these are the 6 hybrid orbitals, 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, we need one more. So 6, one more I am going to draw here. So we got 6 hybrid orbitals. So 6 hybrid orbitals are vacant provided by the central metal atom, and 6 ligands are going to donate its lone pair of electrons to it. Therefore this is from the first F minus, second F minus, third F minus, fourth F minus, fifth F minus and sixth F minus. 6 F minus are going to donate the 6 electron pair to the 6 hybrid orbitals. So how many coordinate bond we got here? We got 6 coordinate bonds. We got 6 coordinate bond. That is how there will be overlapping of vacant hybrid orbitals of central metal atom and filled orbital of the ligands, so that the 6 coordinate bonds are formed. So now we'll see the final point, that is nothing but what kind of hybridization occurred and other properties. Hybridization involved in this particular complex is, what is that hybridization? sp3 d2 hybridization. And what would be the geometry of the complex if the hybridization is sp3 d2? In the previous complex, the hybridization was D2sp3, the shape is octahedral. If it is sp3 D2 also, the shape or geometry will be octahedral only. Octahedral geometry we have. Then we'll see what kind of magnetic property we have. What kind of magnetic property? Of course, the hybrid orbitals are filled with completely, and we don't have any unpaired electrons, but you remember that is only for the hybrid orbitals. These hybrid orbitals are filled, but we have in case of 3D where we have 1, 2, 3, 4 unpaired electrons we have. Since the presence of unpaired electrons in the 3D of the cobalt 3 plus, therefore this particular compound is paramagnetic in nature. So this is a paramagnetic in nature. So in the previous example, all these were completely filled, therefore diamagnetic. Now we have unpaired electrons, that constitutes for the paramagnetic in nature. Now we'll see what kind of complex it is. So now let me write that one. This is outer orbital complex. This is outer orbital complex, and we have one more name also. I hope you know this. We call it as a high spin complex. And now the question arises, why actually outer orbital complex? As the theory suggests us that when n minus 1d atomic orbitals are used, inner orbital complex. When nd atomic orbitals are used, outer orbital complex. Now carefully observe here, we have 4s and 3d, and 3d will be the inner orbital complex. We have not used that. We have one more d. What it is? That 4d. So 2 atomic orbitals are 4d is going to be used for the hybridization. So if this is n and this is n minus 1, n value is 4. In case of 4d, the n value is also 4. Therefore, since we used 2 atomic orbitals of 4d as good as nd atomic orbitals, because of that reason outer orbital complex it is. So remember that when we have weak ligand, the complex formed is usually outer orbital complex. When we have a weak ligand, the orbital complex is a high spin complex, you can say. Remember this, in the previous example we had a strong ligand, pairing occurs. Now we have a weak ligand, the pairing of electrons won't occur, and depending on that one, we create the vacant orbitals, we take the hybrid orbitals and will carry out the overlapping, and we predict the nature of the complex, in particular hybridization geometry and magnetic property. That is about the second example. Next example we'll see, we have a nickel as a central metal atom. Atomic number of nickel is 28. We'll write the electronic configuration of nickel. This belongs to 3d series again. Therefore, the nearest noble gas is argon, and we have a 3d and we have a 4s. Argon, it is 18, isn't it? So therefore, I will write 3d8 and 4s2. 18 plus 8 plus 12, we will be getting 28. So 28 is the atomic number of nickel, and I have written the respective electronic configuration of that. We'll see the oxidation state of nickel. So this is anionic complex, since we have a negative charge over the complex here. So Cn minus, this is a cyanido ligand, and 1 minus for 1 Cn, and we have a 4. Therefore the charge will be 4 minus, and the charge of nickel would be 2 plus here. 2 minus 4, you will be getting minus 2. Therefore we need to write the electronic configuration of nickel with the oxidation number 2 plus. So Ni2 plus. So Ni2 plus means 2 electrons has to be lost. So loss of electron occurs in the valence shell. Therefore, the 2 electrons which is present in 4s is going to lose the electrons. Therefore, the electronic configuration of nickel 2 plus will be argon. We have a 3d8 and 4s0. Now we'll write the orbitals for this one. Orbitals of Ni2 plus. So we have a 3d and 4s. I consider 3d. So this I am going to draw the atomic orbitals for the 3d. Since it is d, therefore 1, 2, 3, 4 and 5. This will be for the 3d. We have a 1 of 4s. This will be for the 4s. Now I fill 8 electrons in the d atomic orbitals by following Pauli's exclusion principle, especially the Hund's rule. The 8 electrons, out of that 1, 2, 3, 4, 5. Now the pairing of electrons starts 6, 7, 8. So that is how I filled with respect to Hund's rule. So now in the 3d we have 2 unpaired electrons. Now the coordination number of this complex is 4. So central metal atom nickel 2 plus has to provide 4 vacant orbital. We have only 1. So one more concept is also important, that is what kind of ligand it is. The ligand involved in this particular compound is a Cn minus. Remember, Cn minus belongs to strong ligand, means the pairing of electron starts. If the pairing of electron starts, then we have 1 vacant orbital and 1 more vacant orbital, 2 more we have. So we needed 2 more. Because of that reason, I consider atomic orbitals of higher energy. After 4s we get 4p. For the p I am supposed to consider. So I have 4p atomic orbital. Now we'll see Cn minus is strong ligand. Cn minus is strong ligand. Now what happens? Electron pairing occurs. Electron pairing occurs. So how actually electron pairing occurs? We'll see now. So now I am going to draw for the 3d. And 3d I need to consider 5 boxes. 1, 2, 3, 4, 5. Let me draw for the 4s. This is for the 4s. and for the P I need to consider 3, therefore for the P, especially for P, I have considered here. So since the presence of a Cn minus, there is a pairing of electrons against Hund's rule. 3 single we have means we get one pair. So this will be as it is. The first 3 orbitals are already completely filled with a pair of electrons. So now these two will undergo pairing. Therefore that pairing I am supposed to write here. So now we have 1, 2, 3, 4, 5 we have. 5 vacant orbital, but the coordination number is 4. Therefore I need only 4. So therefore 1, 2, 3, 4. Only these vacant orbitals I consider. I am going to show it in this fashion to understand what kind of hybridization takes place. So we have this is for the D. So we have 1 D, and this is of the S. We have 1 S and 2 P we have. So DsP2 hybridization. So actually DsP2 hybridization takes place. So now we have 1D, 1S and 2P. These are all atomic orbitals of different energy. They intermix to provide the hybrid orbitals. The number of hybrid orbitals will be as same as the atomic orbitals involved. Therefore 1, 2, 3, 4, we get 4 hybrid orbitals of identical energy. So these 4 hybrid orbitals I am supposed to write here. So 4 hybrid orbitals, let me draw here. So 1, 2, 3, 4, and all these are 4 and DsP2, isn't it? So 4 DsP2 hybrid orbitals. So all these are DsP2 hybrid orbitals. So now these hybrid orbitals are of identical energy. So central metal atom Ni2 plus has provided 4 DsP2 hybrid orbitals. So now we have the ligand Cn minus, 4 Cn minus ligands we have. Each Cn minus contains lone pair of electrons, and totally 4 pair of electrons is going to donated by Cn to the central metal atom. Therefore what I am supposed to write here, 4 Cn minus ligands. 4 Cn minus ligands with 4 electron pairs. 4 electron pairs occupy 4 hybrid orbitals. So now I have 4 hybrid orbitals. I will represent that, and now all the 4 hybrid orbitals are filled with 4 electrons. This is from 1 Cn minus, from second Cn minus, third Cn minus and 4 Cn minus. How many coordinate bonds we got? We got 4 coordinate bonds. Since we have 4 ligands that are going to donate its lone pair of electron to central metal atom hybrid orbitals, therefore 4 coordinate bonds are formed. We'll write the remaining points. So what kind of hybridization is involved? The hybridization involved in this particular example is DsP2 hybridization. And what is the geometry? So do you remember, if the kind of hybridization is the DsP2, the geometry of the complex will be square planar. Geometry of the complex will be square planar. Means if you consider a square, central metal atom will be at the center and the 4 corners of the square are occupied by the ligands. So that is how the geometry of the square planar looks like. Now we'll see what about the magnetic property. Magnetic property depends on number of unpaired electrons. Of course this will be completely filled, and if you consider 3D also, all these are completely filled. We don't have unpaired electrons, therefore this belongs to a category diamagnetic substances. Diamagnetic complex it is. Then whether it is inner orbital complex or outer orbital complex, since a strong ligand I consider, therefore the complex will be inner orbital complex. Or you can say, now here the 3D atomic orbitals are used, therefore because of that reason n minus 1d atomic orbitals are used, therefore this particular example belongs to inner orbital complex, or you can say it as a low spin complex also. This is how hybridization, geometry and magnetic property of this particular compound can be predicted by valence bond theory. In example number 4, we have nickel as a central metal atom and Cl minus chlorido as ligands. We'll see hybridization, magnetic property and the geometry of this complex. Atomic number of nickel is 28. Electronic configuration of nickel, argon, 3D and 4s I consider. Argon will be 18, therefore 3D8 and 4s2 is the electronic configuration of nickel. But the nickel in this complex will be not present as nickel. This is anionic complex, since the charge is 2 minus and we have a chlorido Cl minus as a ligand. Totally 4 chlorido we have. The total charge will be 4 minus. And then the charge of the nickel or oxidation number of the nickel will be 2 plus, because of 2 minus 4 you will be getting minus 2. So nickel present as a nickel 2 plus ion in this particular complex. Therefore electronic configuration of Ni2 plus will be argon. 2 electrons has to be lost. From valence shell there will be loss of electron. Therefore 3d8 and 4s0 I consider. Let me write the orbital of this nickel 2 plus. Orbitals of Ni2 plus. 3d8. So now I need to consider the d atomic orbitals. 1, 2, 3 and 4. This is for the 3D. Now I have 4s and this is for the 4s. We'll fill the electrons. In a D we have 8 electrons. Follow Hund's rule. 1, 2, 3, 4, 5, 6, 7, 8. We have 2 unpaired electrons in a 3D atomic orbital. As per the theory, since the coordination number is 4, central metal atom has to provide 4 vacant orbitals. And the ligand, the type of ligand is weak ligand. Cl minus belongs to weak ligand, means the pairing of electrons won't occur. Therefore we have only 1 vacant orbital. Therefore I consider the next higher energy level. After 4s we have 4p. So now I consider 4p. This will be for the 4p, and for the p we need to consider 3 boxes in this fashion. So now we have 1, 2, 3, 4. 4 vacant orbitals we have provided by the central metal atom. But remember, these electron won't pair because the Cl minus ligand is weak ligand. The same thing I am going to write here. Cl minus is weak ligand. Therefore, electron pairing does not occur. So if Cl minus is weak ligand, as I told you, there will be no pairing of electrons against Hund's rule. Therefore, as same as in case of 3D, let me draw that. 1, 2, 3 and 4. Now let me draw the electrons. 1, 2, 3, 4, 5, 6, 7, 8. As same as the above. Now I consider 4s, which is completely empty. I consider 4p also, which is completely empty. Now we have coordination number 4. Coordination number is 4. Means the central metal atom has to provide vacant orbitals. So 4 vacant orbitals, 1, 2, 3, 4. So this I represent in this fashion to know what kind of hybridization takes place. So all these are the 4 actually the vacant orbital. So what kind of hybridization takes place? This will be S, and we have a p. How many p we have? 3 we have. So therefore sp3 hybridization. So sp3 hybridization occurs. So 1s and 3p are the atomic orbitals of different energy. They intermix to provide hybrid orbitals of identical energy. The number of hybrid orbitals will be as same as the number of atomic orbitals, 1, 2, 3, 4. Therefore we get 4 sp3 hybrid orbitals. So 4 orbitals, let me draw that one. So these are the 4 hybrid orbitals, remember that one. So 1, 2, 3 and the 4. So all these are 4 sp3 hybrid orbitals. From the metal, we got 4 sp3 hybrid orbitals. The energy of these orbitals are identical. Now we have a ligand, that is Cl minus. So 4 Cl minus are going to donate 4 lone pair of electrons to the central metal atom, and 4 pairs of electrons are going to filled into the vacant orbitals. Therefore 4 Cl minus ligands with 4 electron pairs occupy 4 hybrid orbitals. Let me draw the hybrid orbitals. We have 4 hybrid orbitals, and these hybrid orbitals are vacant and they are filled with the electrons of Cl minus. So 1 from 1 Cl minus, this is from 2nd Cl minus, 3rd Cl minus, and this is for 4th Cl minus. We got here 4 coordinate bonds. We got 4 coordinate bonds. We'll write the properties. What kind of hybridization is involved? And the hybridization involved here is sp3 hybridization. What is the geometry of this particular complex, which depends on the type of hybridization. If the hybridization sp3, then the geometry of the complex is tetrahedral. Tetrahedral geometry it is. Center we have central metal atom, and at the 4 corners of the tetrahedron, so 4 ligands will be present. Tetrahedral geometry it is. And magnetic property, that depends on the number of unpaired of electrons. Of course, in hybrid orbitals or are paired, we have a 3D where 2 electrons pair we have, unpaired electrons we have. Therefore, paramagnetic in nature. Since n minus d atomic orbitals are used, or I can say weak weak ligand we used, sorry, not n minus 1d, we have a weak ligand. So weak ligands, if we have, the kind of complex will be high spin complex or outer orbital complex. So based on the ligand I have done. So here in this particular example, based on the ligand, since weak ligands we have, so weak ligands are going to form the outer orbital complex or high spin complex, I can say. So this is how the geometry, magnetic property and hybridization of this particular example I explain. In the same manner, any coordinate complex we have, we can explain the properties of hybridization, geometry and magnetic property using the well-known theory. We call it as valence bond theory. In the next session, I move with one more theory that holds good for coordinate compounds. We call it as CFT, crystal field theory.